So this video is going to go over some tips and tricks and must-knows of the world of logarithms. So let's start in here. I call these our exponent rules just because they're based on exponents, um, but they're just some really cool things. So we know that when we're dealing with a logarithm, and all of these are logarithms, even though this one's an ln, we know that's just a natural log now, is saying what exponent was needed to take this to this. So I wanted to rewrite this first one. I'm saying b to the what is equal to b. Well, we've talked about this before. The only exponent that can turn something into itself is an exponent of 1. So every single time we see this relationship that the base and the argument is the same, we automatically know that that is going to be equal to 1. That does come in handy. So say that we had 3 times log base b of b. We know that this expression is going to equal 3, because it's going to be 3 times, well, this quantity is equal to 1. So that's why these tips and tricks are useful, is because we can then apply them into our world of solving and simplifying. Similar but different, we have the one right beneath it, which is b to the what is going to be equal to 1. So what exponent turns b into 1? Well, we know that to turn something into 1 using an exponent, it's going to be 0. So therefore, this one is always going to be equal to 0. It does not matter what numbers you have here. So I could do log base 3 of 1. It's going to be 0. Log base 1 over 200 of 1. It's still going to be 0. So 0 is that fancy exponent that's going to turn any number into 1. Once again, like above, we could then put that into an expression. So I could say 3 times log base b of 1. Well, I know that this whole expression is going to equal 0 because 3 times 0 is 0. So anytime you notice that your argument is 1, your final answer, your expression answer output is going to be 0. Versus when they are the same, when the base, when the base and the argument are the same, that is when it's equal to 1. So let's look at this one. Here, when we see that it's an ln, we need to recognize that the base is also e. Well, if I look at this a little bit more carefully, it's what we have above. The base and the argument are the same, and so therefore this is also going to equal 1. These two are really the same property. The last way we can see this is the log of 10. We know that if we don't have a base written, that base is really 10. So once again, we see that relationship that these are the same is going to be equal to 1. So these are some of our tricks that are going to be really, really useful as you dive further into your understanding of exponents. Your understanding of logarithms. With that, we can also look at some of these examples. So here it says if the argument is a fraction. So let's come up with an example of that. One that we've looked at before is the log base 6 of 1 over 216. So here, my argument is a fraction. Notice that we are stating then, we're making the assumption that our base is going to be a whole number or an integer here. I think it's a whole number actually. So if our base is a whole number and our argument is a fraction, what had we true about the exponent? Well, we know that in order to make a whole number into a fraction, our exponent originally had to be negative. So that is another one of our kind of tips and tricks to keep in mind. If your argument is a fraction, then you know that originally your exponent had to be negative. And that goes conversely. We don't often see that, but if your base happened to be a fraction and your argument was a whole number, so if one of these is a fraction and the other one isn't, that is always going to be from a negative exponent. The second one is similar but slightly different. So it says if the argument is smaller, the argument is smaller than your base. Well, what we mean by that, assuming that they're both whole numbers. So one of the ones we looked at is the log of 125 of 5. So here we said 125 to the what power is equal to 5? Well, we know that if this is the case, if we're becoming smaller, we're really taking a root. And to take a root, we're using a rational exponent. And rational is just a really fancy way of saying your exponent is a fraction. So a lot of people like to get these confused because each of them have a fraction in them. But that means that the other one's not going to be a fraction. It's kind of my way of thinking about it. Only one number is going to be a fraction in this case. So once again, if I had log base 6 of 1 over 216, only the 1 over 216 was a fraction. 6 and negative 3 weren't. Here, my final answer would be 1/3. That's a 3. So only the 1/3 is the fraction. So these tips and tricks right here are all based around some things that we already know about exponents, just looking at them in a different way. On this side, we have some things that are specific to logarithms. So logarithms you can look at through the scope of a function, so actually graphing them or solving them. In this case, we have to recognize that the argument of a logarithm is always going to be positive. So a must be greater than 0. Notice that it's not greater than or equal to 0. 0 is not a positive number. So in some other things, such as radicals and even indices, we've talked about it can't be negative, and 0 is okay here. But in this case specifically, we're talking about the fact that it must be positive, so it must be greater than 0. So this might be help in finding the domain of a function, or if you're solving things back in order to check and see whether or not they are extraneous solutions, you want to see when you plug it back in, is your argument greater than 0? If it's greater than 0, awesome. If it's not greater than 0, then it's going to be undefined. An example being if I had the log of x minus 2 equals y. Well, if I try plugging in x equals -5, I'm going to the log of -5 minus 2 equals y. The log of -7 equals y. -7 is a negative number, so y would be undefined here. The graph would not exist over here. So, or that would be an extraneous solution if I were trying to solve it out. All right. The last kind of cool trick that we need to know before we move into actual logarithm rules, there's the basic ones, is what's known as the change of base. So our calculators easily do the common log, which is base 10, or the natural log, which is base e. And so we need kind of a cool way that we can translate any logarithm we have to have one of these bases. So there's this change of base formula. There is a way to go through it and prove it. I'm not going to do that right now, but there's this change of base formula. What it pretty much says is you can rewrite any logarithm as a ratio of 2 logarithms. You get to choose what base, but that base must be the same on top and bottom. Most often we use 10 or e, and it doesn't matter which one you do because your calculator can do either of them. What was your argument stays the argument on top. What was your base becomes the argument on bottom. Now, I like to come up with silly things, so I like to remember the base goes on bottom. I do that kind of alliteration there to remind myself that the base goes on the bottom, so I know which one goes where. I'm sorry. So a basic example of what that could look like, we could say the log of base 2 of 5. Well, this is something that I don't know. I do not know what exponent takes 2 to 5. I know that 2 squared is 4, and I know 2 cubed is 8. So I can estimate that this is probably a number slightly larger than 2. It's got to be between 2 and 3, and 5 is closer to 4. I can estimate that, but I want to be more precise. So I want to be able to plug this into my calculator to figure it out. In which case, I need to write it as a change of base. So it says, go ahead and write a ratio and choose which one you want. So I'm going to do the log. I'm going to do a common log. I'm just going to write log on both. What was the base? Goes on bottom, so it becomes the argument on the bottom. And what was the argument? Stays on top. This is an equivalent expression. If I had a calculator that I could type in whatever base I want, and I typed it in like this, or If I type it in using just the common log, I'm going to get the same answer for both of these, which is really cool. I could do it again. I told you the other one we like to use a lot is the natural log. So I could rewrite this as the ln of 5 over the ln, ooh, the ln of 2. All of these are equivalent expressions. So there you have it. These are some tips, tricks, and must-knows of the world of logarithms.